Respected Sir, Ma'am, myself Shraddha from CSC Department of Section F. Today I'll be talking about the normal form of spatial stiffness matrix. Introduction. The spatial stiffness matrix is a fundamental component in structural analysis. It relates the forces and displacements of structure in three-dimensional space. Understanding its normal form is essential for simplifying calculations and interpretations. The example is given, this is the given example of spatial stiffness matrix. A spatial matrix refers to a mathematical or componential structure that represents spatial relationships or data in a matrix form. It is commonly used in fields like geography, spatial analysis, computer science, and physics. Depending on the context, a spatial matrix can have different purposes. Importance of spatial matrix. The stiffness matrix defines how a structure responds to applied loads. It is critical for ensuring stabilities and performance in engineering designs. A well constructed stiffness matrix can lead to more efficient componential methods. Definition of normal matrix. A normal form of matrix is a simplified representation. It captures the essential characteristics while eliminating redundancy. This form is particularly useful in model analysis and dynamic simulations. This in this the following forms are the normal forms of matrix, uh, where IR is the identity matrix of order R, O is the null matrix of suitable order. In any matrix, it is if any matrix is reduced to its normal form, then the rank of matrix will be equal to the order of identity matrix. Structure of spatial stiffness matrix. The spatial stiffness matrix is typically a square matrix. Its dimensions correspond to the degrees of freedom of the system. Each entry represents the relationship between specific displacements and forces. Characteristics of normal form. The normal form typically has a specific structure that facilitates calculations. It often contains diagonal dominance, which enhances numerical stability. The form may include zero entries that reflect dependence between certain moments. Transformations to normal form. The given matrix can be transformed into normal form with various transformations. Techniques such as eigenvalue decomposition are commonly used. Coordinate transformations can also simplify the matrix and enhance clarity. Applications in engineering. The normal form of stiffness matrix is widely used in finite element analysis. It aids in the development of efficient algorithms for structural simulations. Engineers rely on this form to predict the behavior of complex structures accurately. The spatial matrix are also applied in geographical data representation, image processing. To talk about geographical representation or data representation, a spatial matrix can represent geographical features or spatial relationships between locations. For example, adjacency adjacency matrix shows which locations or regions are adjacent to one another. Distance matrix stores distance. Example, Euclidean Manhattan between multiple spatial points. uh, image processing image processing in image processing, spatial matrix concept can be applied. In image analysis, a spatial matrix can represent pixel intensity values in a grid where rows and columns correspond to the spatial coordinates of an image. Challenges in formulation. Accurately deriving the normal form can be mathematically challenging. Uh, but it can be derived by using this formula. in which K is global stiffness matrix, U is nodal displacements which are unknowns, and nodal forces are represented with F. Complex geometrics and boundary conditions may complicate the process. Resources may also limit the feasibility of certain transformations. Future trends in stiffness matrix analysis. Advances in computational methods are improving the formation of stiffness matrix. Machine learning techniques are being explored for automated stiffness derivations. The integration of real-time data is paving way for dynamic stiffness evolution. Here, the categories and algorithms of machine learning are divided into four types: supervised learning, unsupervised learning, semi supervised learning, and reinforcement learning. This unsupervised learning is categorized into two: classification and regression. Unsupervised learning is clustering and association, semi supervised learning is classification and clustering, and reinforcement learning is classification and control. uh, this supervised learning is into four types: linear regression, logistic regression, random forest, network neural. Unsupervised learning is divided into four types: principal component analysis, t distributed, sophisticated, neighbor embedded, association rule. Semi supervised learning is U classify and gate. Reinforcement learning is Q learning, Monte Carlo tree search, temporal difference, and triple. To conclude, the normal form of spatial matrix is essential for effective structural analysis. It enhances numerical stability and facilitate complex simulations. Continued research in this area promises to yield more efficient engineering solutions. This spatial stiffness matrix is still is in research process. Um, this promises to yield more efficient engineering solutions. The spatial matrix are applied in transportation, urban planning, environmental modeling, and epidemiology. In transformation, it is used to model travel distances and routes. In urban planning, study connectivity between neighborhood or regions. In epidemiology, track disease spread using proximity and contact patterns. A spatial matrix is a fundamental tool for representing and quantifying spatial relationships in geographic and spatial data analysis. This spatial matrix is a mathematical structure that is used to represent spatial relationships or interactions between geographical entities such as regions, points, or cells in a grid. It is typically organized in a grid like tabular format where rows and columns correspond to specific spatial units, example locations and regions, and the values within the matrix indicate the nature of the relationship. The components of spatial matrix are rows and columns and matrix values. These rows and columns represent special entities like cities, districts, and grids. Matrix values encode information about spatial relationships which could include adjacency, distances, and weights. uh, there are uh, there are three different types of spatial matrix: adjacency matrix, distance matrix, and weight matrix. This is the summary of spatial matrix. Spatial matrix is a fundamental component in structural analysis. To conclude, this spatial matrix has a lot of uses in engineering world, and scientists are still in research in this area, and as it promises to yield more efficient engineering solutions. These are the examples of spatial stiffness matrix. Thank you.